title is Barracuda, an open source framework for parallelizing divide and conquer algorithm. Okay, we approach the presentation to first decline our motivation and objective. Then we present the design approach and the implementation of the framework. Third, we develop the operating mode and application of the framework on recursive applications like Fibonacci, quicksort, merge sort, integrate, etc., and so on. Following this, we evaluate the performance evaluation in comparison with framework for join framework in Java. And finally, we conclude and have feature work. Okay, what's our motivation? We realize that in Java and generally, the divide and conquer algorithm are not fit for hybrid discrete shared memory multiprocessor architectures. And here we are going to see how we can exploit implicit parallel for loop within multi-way recursive parallel algorithm, and how to explicitly highlight dividing, conquering, and merging processes. This is how framework design. The sequential divide and conquer program is the input. So the objective is how to parallelize the sequential divide and conquer program. And here we propose the architecture, the design of the framework. It consists of extracting divide function, extracting also merge function, and we will have for loop parallelism function. We have the conquer task, which is the task parallelism, and the parallelizing merge function, which is for loop parallelism. And we also have some other built-in functions. And after we will get the parallel divide and conquer algorithm. So this is the architecture, the design of our Barracuda open framework, open source. Just I want to precise that this framework will be implemented in Java. First of all, we want to understand how divide and conquer algorithm is going to the functionality of this algorithm. First of all, we have a big problem. The big problem is split in sub-problems. The sub-problems are rapidly divided in all the sub-problems until we get small sub-problems. After the sub-problems are executed or solved, and after we solve the problems, we get results. Those results are finally merged and repeatedly merged until we get the final result corresponding to the initial big problem. This is the feature of, or the real functionality of divide and conquer algorithm. So here our approach is from a multi-way recursive application. For instance, if you have Fibonacci is a two-way recursive application because the recursive application is called twice. And here our approach is first of all to separate data. It means by data, parameters and return values. Parameters or former parameters of the recursive method. And we separate data and task. Task correspond to called recursive method. After that, we encapsulate parameters and return values within an object we name range BRCT. The divide process recursively divides range BRCD until we get a list of range BRCD. This operation can be done in sequential execution or parallel execution. Here in our framework, we have the choice whether to do the divide process in sequential or in parallel execution. The list of range BRCD is a chair list. This list is shared and accessed by worker threads, which concurrently get elements by the list of compute them. Okay, this list is shared and concurrently accessed. So we need to synchronize the access. After the end of the list is reached, the worker thread maps the result from previous compute. Here we have a schema, a synopsis of our approach. At the figure at left, we have the matrix perspective. So here you can see this is the big problem. At the start, we have the big problem. So remember that I said we make separation between data and call method. Here we are going to handle it data. And here, this is the first range BRCD. Keep in mind that BRCD is the encapsulation of parameters, formal parameters, and return value. After we apply the dividing operation, we get two range BRCD, because here in this example we have two-way recursive method, and at the second step we divide it into two, so we get 4 range BRCD until we have the number or the list of range BRCD we want. So here we have the possibility to define the performance parameter, which is named the number of tasks or the number of range BRCD. This is the final list, and this list is a list of range BRCD, and this list is concurrently accessed by different work threads, and this list needs to be synchronized. But we have two kinds of synchronized. We have blocking synchronized and non-blocking synchronized. In our framework, we'll use non-blocking synchronized because blocking synchronized is a time-consuming and can impact the performance of the execution. At left, we have the figure where the framework is, or the graph is represent like a tree. Okay, this is the big problem. This big problem is a deferred dividing process is divided into two sub-problems, and so on until we get the final list. Here we have different steps. Here we have 1, 2, 3, 4 steps, and we have the final list. This is an example of a multi-way recursive method. Here we have the method with different formal parameters. We have n formal parameters, and each call method return a result value. Okay. How we encapsulate the formal parameters and return values. Range BRCD is made up of recursive methods, formal parameters, and result if so. Because in some situation, we can have recursive method which don't return values. Okay. In the case of we have return value, the range BRCD is made up of formal parameters and result. Okay, you see here, we create in our framework, we create the class which name range BRCD. And here we have the declaration of different parameters. You see here we have the declaration of result value. And we have steps and indexing and list of range BRCD. Here we have different step BRCD. Here we have the step 0, the step 1, the step 2, and the step 3. In each step, we have arrange array BRCD. Arrange array BRCD is a list of BRCD. And we will consider the last list, the last list of BRCD, which will be the list which is concurrent access by different worker threads. The operation of dividing arrange BRCD into Kawai BRCD, range BRCD. So here we have we explain the divide process. For the divide process, first of all, we have divide BRCD. Divide BRCD is a function, is an empty function. Here the user have to customize and make the content. The content of the recursive method will be copied into this function. Okay, and we have the final divide BRCD. The final divide BRCD will call the divide BRCD, and we have the possibility to parallelize the divide BRCD. Here we have a sequential execution. Here we have a final execution. The advantage to enable final execution of dividing is in the context of a divide and conquer algorithm, where the algorithm spend much time to divide. The fact to get parallel final divide process allows to optimize the execution. Here we have the shared queue of range BRCD, or the list of BRCD. Okay, this is the final list of BRCD. This is the list or the queue which is shared by different worker threads. And here, in opposite of fork join framework, or because in fork join frameworks we have not one shared queue, we have different private queue. Each worker thread has its own queue, and if a worker thread ends up executing and have no job to execute, this worker thread will steal another worker thread from another work array. Here it's not the case. Here we have a unique queue, and the queue is concurrently accepted. Normally we must synchronize this. Here we will use atomic synchronization. The advantage of atomic synchronization is this form of synchronization is non-blocking. After that, after the worker thread and the executing the different job or the different range BRCD, they merge, they execute the merging step, the merging process, and they execute the merging process until they get the final result. And here too, we have two functions: final merge BRCD and parallel final merge BRCD. Here too, this function is sequential. This function is parallel. We have the possibility to enable or disable the sequential or parallel final merging, because we can have some situation where dividing process spends much time to be executed. In this context, it is good to parallelize the process, the merging process. And we have the computing. The computing is the conquering, the step where the different work threads execute their different job. Here we make the comparison between Barracuda implementation versus fork-join implementation. Because fork-join is a baseline in framework in Java. Here we have the process, the step of dividing. In Barracuda, this process is execution by phases. So every step, there is a rendezvous or a barrier synchronization. So before we go to the next step, all process in this step must be executed. After that, we go to step +1. In opposite, in fork-join, this operation is asynchronous. But in the process of dividing in fork-join, when dividing a job, the thread or the task does not need to wait for the others to finish. Here, this is asynchronous. Here, this execution is made in phase. And here we have the possibility to enable or disable. Here, this is parallel. For the queuing management, we have in Barracuda co-sharing. So the queue is shared between worker thread, and here we have private queue. And here we have work stealing. So in work stealing, there are some synchronization costs, because the fact that a worker thread steals a job from another queue, this has some cost. In opposite here, in non-blocking synchronization, generally there is no cost. In the conquer process, here the execution is done in parallel. And finally, in the merge process, here the execution is done in phase. In fork-join 2, the execution is done in phase. Here too, we have the possibility to enable or disable the parallel merging. Here we have just the possibility, it is just done in parallel. After we implement our framework, what is the operating mode and what effort does the programmer must do to exploit or to leverage the framework? First of all, we must copy the content within block, the content of divide and conquer via CD. The framework is available in GitHub. We have to copy it and to insert it just after the recursive method block. And after that, the only effort we have to do is just to copy, pass, or comment out. Here, we have to copy and pass formal parameter and return variable declaration of the recursive method with the range BRCD. And in the task BRCD, we call recursive method with actual parameters preceded by range array BRCD I dot. After that, we copy and paste the content of multi-way recursive method within divide BICD function. Here, the user must have to do some effort in the divide BICD. And after we copy and paste content of multi-way recursive method within merge BICD. Here too, the user must make some effort to do something. Repan range BICD dot to the original former parameters and replace it written by range BICD dot result. And comment out the call main recursive method, declare a new range BICD with the actual parameter of the call recursive method. Call the compute BICD method with range BICD number of threads, number of tasks, and carry actual parameters. Those parameters are performance parameters. So if you want to execute, we have to determine the number of threads depending on how many processors are available in our target architecture, in our target computer. We have to determine the number of tasks and the Kawai actual parameters. So for instance, if you have Fibonacci, the Kawai actual parameters, K is equal to, in Strassen matrix multiplication, K will be equal 7. Here we prove and validate the framework effectiveness by using the framework to parallelize applications such as Fibonacci, two-way recursive, integrate, quicksort, merge sort, Strassen matrix multiplication, which is 7-way recursive method. Here we present the performance evaluation by using our framework in a server which have 8 processors, and we compare the performance of our framework to the performance of FogJam framework. And here we realize that in quicksort and merge sort, our framework lost a little bit, minus 2%, minus 7%. Here for quicksort and merge sort, FogJam framework outperforms our framework. In opposite, in Fibonacci, Strassen matrix product and integrate, we have some performance gain. For instance, in integrate, we have plus 14% compared to FogJam framework execution performance. How we can analyze this performance? We realize that here quicksort in dividing process, because in quicksort algorithm we have to choose a pivot, and depending on the choice of the pivot, we can have balance or imbalance or irregular balance. Okay, this process in quicksort, the fact that dividing is a time consuming. Okay. In opposite, merge sort, Strassen, Fibonacci integrate does not need any time to do the divide, and all are time consuming in Concur. But in merging operation, merge sort and Strassen take much time to merge the results. In opposite with quicksort, Fibonacci and integrate. Here we realize that quicksort, merge sort, and Strassen are memory bound. Fibonacci integrate are CPU bound. Some divide and conquer program spends slight execution time during dividing process. Here, for instance, in quicksort, the fact that we have the possibility in our framework to enable or disable sequential dividing or parallelizing. Here we can use parallel dividing in our framework. In contrario, we don't need to use parallel divide in merge sort, stratisend, Fibonacci integrate, because those algorithm in the process of dividing don't take enough time. We prove the effectiveness of our framework because the framework is available at this address. You can go to this address, and if you want to try the framework, and the framework really works. We easily use the framework to parallelize applications such as Fibonacci, quicksort, merge sort, integrate, stratisend matrix multiplication. The Barracuda framework performance sometimes outperform Java fork-join framework. For instance, in integrate, Fibonacci, stratisend matrix multiplication forces algorithm, our framework outperforms the fork-join framework. Because of the divide, conquer, and merge processes are made explicitly by the framework, then this one can leverage a hybrid discrete shared memory architecture. Here with our framework, the fact that we explicitly extract the divide process, we can get for loop parallel of task of job. And in the context of hybrid discrete shared memory, we can split the list of job and distribute them to different nodes, to different shared memory architecture. And each shared memory architecture have to execute in parallel the job. Because of the framework is open source, it can be used by the community to improve it. Okay, the framework is open source. The community can use it to improve it or to improve it. Thank you very much. If you have some question, thank you very much.